Sorry for the delay. And here we go with lecture number 10. Announcements. Homework 3, due tomorrow, but submit it tonight. You get bonus points. Also, please look over homework 1 and lab 2 so you can fill out any regrade requests that you have. Those are due tonight. And project 1, which is kind of like a really long homework in its format, is going to be released on Friday, and you can work on it with a partner from your lab. So when you go to lab this week, there will be a chance for you to get matched up with a partner. Please go to lab this week, find yourself a partner in your lab, and then you'll be all set to start the project, which will be released on Friday. There's also a guide to using arrays. So if you're feeling a little shaky about what you can do with an array and how, check out the guide. There's also quite a bit of information in the textbook. I hope you're doing the reading. You know, students who do the reading tend to understand things quite well in this course. So I would strongly recommend that if you haven't been doing the reading, now is a good time to start. Okay, so we're going to do an extended demo to begin with that shows off two things. One, a little bit about defining functions and applying them, which is what we covered at the end of lecture last time. And two, a preview of some of the inference that we're going to perform later in the course, particularly about making predictions. So there's a whole unit on making predictions at the end of the course, but why not get started now, and then we can build on that later. Blah, blah, blah. Here's a data set that it's been in, you know, most every statistics course ever taught, I think. It's a collection of measurements of the heights in inches of different children, as well as their mothers and fathers, collected long, long ago. A question that you might ask is there information about the height of a child if you know the heights of their fathers and their mothers? And here's some other information. So this is the number of children in the family where this data was collected. The order is the birth order of the child of interest, and sex is the sex of the child. Now, one way to go about this is to see if there's an association between the height of the parents and the height of the child. But the height of the parents is 2 numbers. We're just going to simplify our lives a little bit and try to get that down to 1 number by averaging the heights of the parents. Hopefully this is something we know how to do right by now, but we will practice it. This involves getting an array of the father heights, getting an array of the mother heights, adding each corresponding element together, and then dividing each entry by 2. And here we're just going to build a table. Empty table, except it has 3 columns: the parent average, the child height, and the sex of the child. Okay, so far? What kind of visualization would help us figure out whether there's an association between the parent average height and the child height? Those are 2 numerical variables. So we use a scatter plot. And here in this old data set is what we see. A big round blob, except it's not quite round. It's sort of oblong. And it does seem like maybe out here in the lower average parent height range, there are slightly lower average child heights than in the high average parent height range. So perhaps there is an association here, because there's some structure to this where as you move from left to right, you also see some trend from bottom to top. But it's an awfully noisy trend in the sense that, like, if you pick any particular, here's some tall parents, less tall child. It happens all the time. Or, you know, like the variability between the children for average parent height of 70 inches is just huge. And that's just how it is with people. And I think the other thing that's interesting to notice about this is that sometimes you think about averages as like typical, Like if we average child heights, it's like somewhere in here. And you might think, oh, like that's normal or something like that, but it's really not. There are very few people at that average height, you know, way more people are higher than that or lower than that than right at the average. So an average isn't really telling you what a like prototypical person is like. It's just telling you somewhere in the middle of a very variable characteristic of people. And by the way, this was all collected before modern nutrition. So I don't think that this is useful at all at telling us anything about how people are today, but it was something that was classically studied. And these are in inches. So 60 is 5 feet and 72 is 6 feet. I said I was going to do something about prediction. So what kind of prediction problem might we arrive at? Well, let's say we find some parents and they're expecting a child. That child is not going to grow up for a long time. Oh, I forgot to mention a very important characteristic of this data set. Very important. These heights are of adults. It says child because they are children, but they're not children in the sense of being young. They're children in the sense of being offspring. So this is the height of adult children, and this is the height of adult parents. Very important piece of information. That's why there's no children that are like, 27 inches tall, because they've grown up already. Okay, so back to the prediction problem. Have some parents, and they're expecting a child, and they're wondering how tall will this child be when it's old? Well, the answer is we have no idea, right? But they might want some kind of guess. Well, one thing you could do is just look at all the children in the world and say like, well, it's just like any other child. So it's going to be somewhere in this huge range of 55 to 80. And they say, but what about our heights? Isn't that relevant? Well, it might be because there's an association between the average parent height and the child height that you could make a slightly different prediction based on the information that you have about the parents themselves. So how might we do that? Well, measure the parents, average it. Let's say we get 68 inches, so 5'8" is an average. Let me show you what about the scatter plot might tell you something about parents from long ago when this data was collected who have a child, but the parent average height is 68 inches. Well, there's a bunch of other pairs of parents that have had children before that also have an average height of about 68 inches. Here we've gone kind of down half an inch and up half an inch, from 67.5 to 68.5. And now we're looking at part of the scatter plot, just the part that contains the children of parents who have an average height of about 68 inches. So this is interesting. Maybe the thing we could do to predict is just ignore everybody outside of these two bars and ask ourselves, well, like what's a average height of a child from parents whose average height is about your average height? What's the math look like? First, we start with all the heights. Now we look at only the subset where the parent average is right around 68. So 68 minus 0.5, 68 plus 0.5. How about that? Thank you. All right. Now we're down to 185 rows instead of the original 934. This is all about, like the filtering we've done is just using the parent average column, but what we're interested in is the range of heights for the children. We know it's a huge range, goes all the way from 60 to almost 80. But if we wanted to just like pick something in the middle of that range, we could take the average or the mean. So we could take this assign it, what's a nearby, and then the mean of the children of all the rows that are nearby to the particular parent average height that we're interested in is np.mean or np.average of the nearby table's child count. So now I'm going to plot the same scatter plot as before, the same two red lines as before. I'm going to add one dot. This adds one dot. And that dot is the average of just the blue dots within the red bars. This seems like a reasonable guess of an average height of a child of, I mean, it is an average height of the children of parents who were about 68 inches tall on average themselves. So if a new pair of parents came along and they were 68 inches tall on average, and they had a child and they wondered, you know, well, how tall is my child going to be? Well, this seems like a reasonable guess. But it's going to be wrong, right? Because they should know in advance that many such children were much taller, many such children were much shorter, and so believing in this one number is useless. But if you had to like pick something that was in the middle, well, that's what we came up with. Questions? Uh-oh. What have I done? Why are there no questions? Okay. Oh, there's a question. I'm saved. Okay, hi. Oh, great question. So like right now we haven't even considered whether the child is male or female. I will get there. That's an excellent point. I did all this work just for parents whose average was 68 inches, but now I'd like to generalize to an arbitrary average parent height. For that, I need to define a function. If I'd like to predict the adult height of a child based on the parent average, then I need to do the same thing, but not always have the parent average be 68. Instead, I want the parent average to be whatever the parent average is. And then I need to make sure that after I've defined all the work that my function does, I say what it returns. So I did it in this way to show you that this is a very common way of defining a function. It's just to get it working for an example and then try to generalize to new examples where we take in some unknown, some variable, and we perform the same arithmetic that we did before. And now when we call predict on 68, we should get this average height, which I think is about 67 or so, 67.62. And what if the parents were taller? Precious. Why did you do that? Maybe there aren't parents that tall. Oh, that's the problem. Look at 72. There are no such parents. Okay, how about 70? How about 70? Oh, so if the parents are 70 inches tall on average, and their kid is, oh, less than 70. That's interesting. All right, let's pick another range where this actually exists. How about 66 and 64? So if your parents' average height is 66, then your kid's average height is 66. And 64. Well, if your parents' average height is 64, then the children's average height is, well, not 64, 65. So it seems like on the low end of the range, this is a little bit higher than what we started with. And the high end of the range is a little bit lower than what we started with. And somewhere in the middle, it's about the same. What if we just tried it for, I don't know, everything? predicted heights equals heights dot apply predict to the parent average. What this says is, please take my predict function, and instead of just trying it on 64, 66, 70, and 68, try it on every parent average in the entire data set. This gives me an array. An array of predicted heights for each entry, every row in the data set. So, since there's one of these per row, it seems like we should just put it in our table. Take our heights column and add a prediction. This is the guess, just by looking at the parent average, of the average height of the child Now I can draw a new scatter plot. One that doesn't just show the parent average and the actual adult child's height, but also shows the prediction that we made by averaging. And here's what we get. The blue dots are exactly the same blue dots that we had before. The gold dots, in this case, are, for each point, what is the average height of children for all the parents that have about that same parent average. So blue dots, easy to interpret. One per child. Gold dot, a little bit harder to interpret. One per child, but it has nothing to do with the child itself. It's just the average child height of all the parents in the data set that have about the same height as the parents of that child. This is called a graph of averages. And what's interesting about this particular data set is that it's pretty close to a line. And we'll study this line. This is called the regression line. We'll figure out how to find an equation for the line itself later in the course. But what I wanted to show you now is just that when people describe an association between two variables as linear, really what they're describing is that if you took little slices along this horizontal axis and then computed averages and you drew those averages, you'd get something that looks like a line. And this is what's called a linear association, linear from the word line. And what's interesting about it is both that it is fairly straight, though not perfect, and also that it has that characteristic we described, which is that if you go way out to the right, 70, what you get here is below 70. And when you get way out to the left, like 62, what you get here is above 62. Meaning that if you look at an extreme point on the horizontal axis, and then the corresponding place of the graph of averages on the vertical axis, it's closer to the mean of the vertical axis than you might expect. And this is actually has a name. This is called the regression effect, and is true of many different data sets. When you make predictions, you shouldn't just predict what the input is. You should kind of move everything toward the mean. We'll learn about it more in the later class. Okay, so two things went on here. We tried to figure out how to use a function in order to generalize something that we had already done for a specific case. We did it for 68-inch tall parents, and then we generalized to parents of any average height. We then use that function over and over again to make an average-based prediction for every single child in the data set. And then we drew the scatter plot, found this graph of averages, and oh, it turned out to be a line. The fact that it's a line is a property of the data. It's something about heights of humans. You wouldn't always get a line. So you could run this procedure on any data set, but you might get some crazy curve, or you might get a flat line. It really depends. If you have a line with a slope, that's what's called a linear association. Question? Okay, very astute observation that I slipped in something that I don't think was ever described to you before, which is what happens when you call scatter with only one argument. What that does is put that argument on the horizontal axis and all the other columns of the table on the vertical axis. So if instead we had just scattered 0 and 1, we'd get that, scattered 0 and 2, we'd get that, but if we want both of them at the same time, then we can leave that out and get them. Not an important detail, but thanks for bringing it up. Cool. So why did the prediction become a different color? When you do this, plot all the different columns, and it just picks a different color for each column. And of course, we pick blue and gold. Okay. And there's a question about what's the difference between mean and average. They're the same. Okay, excellent questions. I want to point out another property, which is that when you have a question, probably a bunch of other people have the question too. And I think that's exactly what happened here. You asked that question, it was great. And I looked in the Q&A and a bunch of other people had it too. So if you do have a question, don't think you're the only one. Probably somebody else has this question too. And if you ask it, then like lots of people will be happy that it is answered. Okay, so there was some stuff here that I didn't explain very well, and that's fine. This is actually just drawing stuff on top of the graph. You don't really know how to do this, but I'll just run through it really quickly. This is the line width. So we were just trying to make these slightly wider lines. And this plot is basically just picking out these 2 points, pop, pop, and then draws a line between them. And the next line picked out these 2 points, pop, pop, and drew a line between them. And here we did a scatter diagram of just 1 point, which is how we drew a dot. Maybe not the best way to draw a dot, but it is it's reasonable. Okay. And this made it big. We wanted a big old dot, size 50. How good are these predictions? Well, we could figure out if they're ever wrong. Here's another opportunity to use a function. What's the difference between x and y? It's x minus y. What we could do is take the heights table, which has the actual height of the adult child and the prediction that we made, and compute the difference. There they are. We'll call these the errors, prediction errors, how different the prediction was from the truth. Let's put that in our table. The child was 73 inches tall. We guessed 70 inches, so we were wrong by negative 3.1 inches. How do we learn a lot about these errors? Well, we could draw a histogram. So we see that sometimes we're right. But sometimes we make a positive error. We guess that the child is taller than they actually were. And here we made a negative error. The child was taller than the average. What's interesting is that this is balanced. You know, it's like about as much area above and below zero. And that is a consequence of the fact that we use the average to make the prediction. You pick the average, and some are going to be high, and some are going to be low. Now, how far off we are is really a property of the data. It's like, how much variability is there in people's heights when you already know their parents' height? And the answer is a lot, plus or minus, you know, not usually 10 inches, but very often up to 5 inches. Now we're finally going to get to your question. Why have we been ignoring the sex of the child the whole time? Well, one thing we can do with a histogram is to group the data first. In this case, we'll group by sex, which is either female or male in this data set, and draw two different histograms. The histogram of the errors that we make for males and the histogram of the errors that we make for females. Stare at this picture for a minute and figure out what it tells you. All right, talk to the person next to you. This is like a 1-minute exercise. What facts about all of our work have we learned by drawing this particular picture? All right, let's wrap it up. Anyone want to offer an observation? It's a big room, I know. Okay, I'll raise my hand. I'll offer an observation. While there are some differences, there are also some similarities. You know, this golden histogram is roughly symmetrical, not entirely, but roughly symmetrical. And it has a width of, you know, about 12 or something like that. The blue histogram is roughly symmetrical and has a width of about 12 or something like that. And so it seems like it's sort of the same picture, but split. For the female children, the guess, we made positive errors. Here's 0. Most of the errors are positive, meaning we're guessing that they're taller than they actually were. For most of the male children, here's 0. Most of the errors are negative, meaning the children were taller than our guess. And our guess was an average among the two sexes in the data set. So, can we somehow like take sex into account when making predictions? And do we think we'll make smaller errors on average when we do that? How would we take it into account? I think it's an interesting question. And one way to take it into account is just to make a prediction that's a little bit smarter than the one we did before. We could take the average height of the parents, but also the sex of the child. Let's take our old predict function. We get all the nearby parents, but now I think what we want to do is limit ourselves to just the children who have a matching sex to the particular choice that we make as the input to the function. And then we use that to compute our mean. So what we did here is instead of taking all the rows for similar parents, we've now taken all the rows for similar parents in height, similar children in sex. This is a 2-argument function. The parent's average height is is 68 and the child is female, then screwed that up, didn't I? Then we get an average height of female children of 64 and an average height of male children of 70. Okay. So maybe we should have new predictions. Heights.apply. Here's where we have to think about the code a little bit. We're going to apply the predict smarter function, but now we have to apply it to two different columns. Parent average height and the sex of the child. We claimed they're smarter. Oh, how do we know that they're smarter? Well, one thing we can do is look at the errors, right? So now we have errors that come from applying the difference function to the difference between the truth. Well, let's do the smarter prediction. Smarter is not a word here, smarter prediction. And the truth, which is the actual height of the child. Put that in our table. Smarter errors. And now it's time for a histogram. Heights.hist smarter errors. What does it mean for an error to be smarter? Well, hopefully it's not as wide. Let's compare this to our original errors. It really is not as wide. Everything is kind of between -5 and 5 with a real concentration in the like -3 to +3 range, whereas before we were way outside the -5 to 5 range. And by the way, before, when we grouped by sex, we saw different errors for the two sexes. How about if we group by sex for our smarter predictions? Well, we're making similar kinds of errors in both cases. You still can't predict how tall a child will be, but you can get a little bit closer on average by taking more information into account. Okay. That's kind of the end of the demo. Questions, comments? Kind of quiet. Okay, I'll teach you something new about programming, and then we'll use it next time. You're gonna learn about how to group. You saw this a little bit, I think, when we built bar charts that showed you the distribution of categorical variables. But now we're gonna learn more about group. Group aggregates all rows in a table with the same value for a particular column into one row. So there were many rows that are now collapsed into one row. The first argument to group tells you which column to group by. There's a second argument, which is optional. So far, we've never seen it, but now I'm going to show it to you. The second argument tells you how to combine the values in all the other columns. This is a very boring table that you've seen before. There's a flavor, and some flavors are repeated, and there's a price. If you just write cones group by flavor, then it ignores the price entirely and just tells you the count of the number of rows. So an important property is that you get one row for each unique flavor, because we passed in flavor. And another property is that we've somehow lost the price. But sometimes you want to know something about the price of all the chocolate cones. And group lets you do that too. So when you group by flavor, and you say, here's what I want to do with all the other columns, I want to average them, then what you get is one row per unique value within the flavor column. It always excites me when that happens. And for all the chocolate rows, what was the average price? This is a hugely useful operation for taking a table that's got one row per individual, and now you're building a new table with one row per possible value in some column. Why did the price get averaged when we never said anything about the price? What this does is say, here's how you should combine all the other columns. So all the other columns, in this case, there was only one. And you could do other stuff. You could do the min. That's the cheapest chocolate you can get. Here's a new thing. You could get a list. List tells you all the different prices in a price list column. This is actually just one column full of lists. Here's something else you can do. You can get the length of that list, which is basically just the count. How many different prices there were. So len would give you the number of grouped values. That's the count. That's kind of the default if you don't actually pass anything in. List tells you all the values. Sum would give you the total, or average would give you the average, or min would give you the minimum. You can pass any function you want that can take a bunch of values and aggregate them into one. Anything that can take an array. Practice a little bit. Here's our welcome survey. You saw this before, right? Yeah, you took the survey. But I think Swapnil did some demos for this before. There's like an extroversion scale of 1 to 10 question in there. And there's the histogram of the distribution. If you group by extroversion, then you just get the counts that correspond to the heights of these bars. But if you group by extroversion and then say what I want is average values of everything else, we get some interesting stuff. We say for everyone who said my extroversion level was 4, the average number of textees was about 5. The number of hours of sleep was 7.2. And you can look for associations. Do it in steps. We've done the grouping. Now we give this table a name. Then we can plot it. Number of textees average. We see a pretty strong association. This is not quite linear, I don't think, but it's sort of linear-ish. An association between the value that people reported for their extroversion and the average number of textees. Just very similar to the line you would draw through the scatter plot of survey.scatter extroversion number of text. Capital letter. Except this scatter plot is extremely hard to read. Whereas once you do the averaging, you can really see the trend. Okay? I said something about lists. This is a programming concept. It's not something we're going to spend a lot of time on. But a list is a sequence. You can't even see my cool title. A generic sequence. What does that mean? An array has all the same kind of thing in it, like all numbers. A list, you can mix and match stuff. You can have a list with a number in it and a string. You can even put a table in a list if you really wanted to. So a list is a sequence of values, but the values can have different types. They're good for representing rows. Because a row in a table might have a string for the name and a number for the height or whatever, right? So you can have kind of a mixture of different kinds of values within a row. And if you create a table column from a list, it will be converted to an array automatically. I don't think it's really worth showing you a demo. I was just going to type this out. But you can see what it does. It makes a list, that's what the square brackets do, of a number 5, the word 4, and a table. Why are lists useful? Well, they can make rows. They can also do one more thing, which is that they can allow you to group by 2 columns. So here's a list. This says group by both handedness and sleep position. That's first background. What happens if you group by just handedness? You get left-handed, right-handed, and both. What happens if you group by just sleep position? You get 4 different options. What happens if you group by a list containing 2 different labels? You get all possible combinations of a value from handedness and a value from sleep position. This is called cross-classification, or grouping by 2 columns. It allows you to look at 2 different variables at the same time, in this case, 2 different categorical variables, and get a count for each combination. The group method can aggregate all rows that share combinations of values in multiple columns. So what we've done here is just say which columns to group by. And this is actually just one argument. It's a list of the labels of the columns that we want to group by. It is possible to add a second argument. You ready for this? Once I do this, I want to average everything else. Every combination of handedness and sleep position. Now I know their average extroversion, their average number of textees, their average hours per sleep. So maybe with this table, you could ask questions like, if you sleep on your dominant hand, do you sleep longer or less long? That's the kind of thing we're after here. So if you're left-handed and you sleep on your left-hand side, your average hours per sleep is 7. If you're right-handed, I got to show the whole table. If you're right-handed and you sleep on your right-hand side, well, your average number of hours per sleep is 7.1. It's so comfortable, I guess, on your right-hand side. You might ask yourself, like, is 7.1 really very different from 6.97? Is this kind of just like in the noise, or is this an actual difference? And that's exactly the kind of problem we'll try to answer in the second unit of this course about inference. Right now, we're just looking for differences and how to do that. And group is a powerful tool. We'll pick it up again on Friday and investigate a little bit more. See you soon.